Okay, so this seminar has ended up turning into sort of a mini course, which is fine. I mean, there's that quantity of material, but as we observed, the audience thinning out, so this will definitely be the last installment. First thing I wanted to do was jump back a little bit to an earlier part of the story. There was something that I didn't talk about earlier, and since we had the time, I thought it would be a little interesting just to kind of give you a flavor of something of kind of like the way these computations, the way I managed to pull off these computations in detail, by keeping track of all the details. So there was some spectral sequence and, what it was computing, you don't need to remember, and it's not going to come up again later today. But basically, there was this thing with the HIs and some spectral sequence. And I said that, well, if you work over A of 3, that in effect, it's like truncating it. You just take these first 4 stages. And I carried out the computation completely for A of 3, and I completely finished it. Okay. And okay, so that was so again, what that computes is not so important, but let me show you a picture of what it was. And then this is the chart. This is what the complete answer for A of 3, it's some invariant of the Coleman of A of 3 that I computed here. Okay. And so there's a lot of elements on here, and how do I keep track of them and organize them in families and so forth. So that's what I wanted to show you just a little bit about like what's kind of goes, what's going on behind the scenes here. I show you these pretty pictures, and this is what I did, but how do I actually get there and keep track of all the elements and not forget things? Okay, so I'm going to.
4, I mean, an 8.
Right. So the C naught
arrow above it.
So the arrow, okay, so remember there was this funny like degree shifting with doubling and undoubling. And these vertical arrows really mean H1 multiplications. And then the lines of slope 1 mean H2 multiplications and so forth. So that's really what so it's saying it's an infinite H1 tower on C0, which is sort of a familiar like motivic.
So in A3, there is an infinite tower in 16. Which an H naught tower in 16. Which I'm not seeing here.
That's because it's not in Chow degree 1. This is only part of, I'm not computing the Coleman of A of 3. I'm just computing one particular part of it that was relevant for some reason that was relevant 3 weeks ago and isn't so important right now.
Okay.
The point that I'm trying to make is to say, like, how would you kind of keep track of all these elements? So let me show you how I actually do this. Okay. And in practice, what I do is a lot of work with spreadsheets. Okay, so this spreadsheet is keeping track of all the elements in the spectral sequence. And the way that the basic philosophy of the spreadsheet is that it keeps track of every element in the spectral sequence exactly once. Not like, not with no redundancy, with no missed elements, and with no redundancy. So in some sense, it's like an additive picture of the spectral sequence.
That's
okay.
F2 basis.
And well, yes, but you can't like an F2 basis. Ideally, you use an F2 basis. The problem is that there are actually infinite elements, like you have infinite H naught towers and things. And so you can't literally do an F2 basis because it's not finite. So you have to encode it a little more generally. Okay. And that's precisely the point that I wanted to show you. See, I've got these columns here, G torsion and P torsion. And first of all, the numbers represent like, how many G multiples an element supports, but I'm using kind of like the convention like we do with characteristics of fields, where 0 really means infinity, right? So that's when we talk about a field of characteristics 0, it's anyway, okay. So that 0 means, so when I say that this element is P torsion 0, what I mean is it's an element and infinitely many P multiples, P times it, P times that, and so I'm keeping track of the elements in infinite families, but I'm still keeping track of every element exactly once. Now, if you look closely at this chart, you'll see, wait a minute, there's something funny here. Like, for example, here's this V naught times 1, and I'm saying that it's G torsion 1, so as if it's annihilated by G. But then here, there's V0 times G. So clearly, V0 times 1 is not annihilated by G. It's actually, there it is. There's V0 G. And then that guy has infinite many G multiples. Well, the point is that for technical reasons, what I had to do is I had to, sure, there's V0 times 1 and all its G multiples, but I have to handle the first one separately because the first one behaves a little bit differently than all the rest. Okay, so what I did, so when I say that it's G torsions 1, what I'm really talking about actually is an associated graded. In an associated graded, this guy is G torsion, and then the infinitely many G multiples are handled here. Okay? But an associated grid preserves the additive. It's still kind of, it's okay on the additive structure, so I'm keeping track of all the elements. So this one really means just think about this element V0 times 1 and don't worry about the G multiples. The G multiples, if they're non-zero, are handled somewhere else in the spreadsheet. And in particular, they're handled on this other one.
Wait, where does? How does, it's the one there would say G V naught is 0.
But that's what, but what I,
And, for some elements, the one in that column means G times that element is 0, like GC is 0, for example.
so it doesn't really mean that, but it is in fact true. What the one means is don't worry about the G multiples of this element C. If there are G multiples, they'll be somewhere else.
So there are never any 2s in this column.
It turns out, because of the way this calculation works out, there aren't any twos, but there could be twos.
In which case, G times it would be in that row.
Right.
and G squared times it would.
Could be.
Not exist or be somewhere else.
Right, it would be somewhere else,
So
exactly.
this is how John and I describe the F2 GW1 W2 structure.
Yeah,
So that, you have to deal with H naught because it has a different annihilator and then H naught squared,
Right.
then H naught cubed, and up they're all the same.
yeah, right. So it's just, as I say, this is like a bookkeeping skill.
What I
for
was
this type.
curious about is what you did when the F2 rank was greater than 1 in a by degree where the F2 rank is.
Oh, so there would just be two, this guy's at degree 20,4, there'd just be another line with 20,4 on it. There'd just
And
be
then
two.
so you have to talk about the sum of those two.
So this is, right, so then you have to keep track of that, so this is a basis, right? And so if you need to talk about the sum of it, you might need to change your basis or do something, so you have to be careful about that when that arises.
Well, there are situations where there is no one change of basis, though, but,
That'll take care of everything, yeah, right, I agree, so you kind of prioritize what's most important, and then, if you have to add notes over here on the far right, then you do that, right? Just to keep track of what's
you
going
just
on.
take a note that this guy is the sum of the previous.
Right, or something like that, right? And then, and ultimately what do you, this is supposed to be a page of a spectral sequence, and so what they're gonna have differentials, and certain elements are gonna cancel out other elements with differentials, and so you're gonna be like deleting 2 rows at a time. Roughly speaking, when you turn the page of the spectral sequence, that involves deleting 2 rows of the spectral sequence at the same time. You delete the source and the target and then you're getting an additive basis for the next page of the spectral sequence, okay?
Or you might actually take 2, 3 rows out and add 1 row in.
Well, yeah, that's what that change of basis would be, exactly, right? You could that's exactly the kind of thing you do in practice when things get complicated, you do that kind of thing. Right. Okay, so this was a kind of a short little self-contained discussion, to show you a little bit about like what goes on, like, the talks are these nice presentations, but they don't really reflect the daily reality of doing this kind of mathematics. The daily reality of doing this kind of mathematics is staring at these kinds of spreadsheets and organizing them in a useful way and figuring out how to encode things so that you don't confuse yourself, right? And when you get confused and tangled up, then you have to start over again and with a better, more robust bookkeeping system, right? Okay. All right, so that's that. So, yeah, so do you remember where I was just showing you a minute ago? I had this 4 copies of X, right? This is indexing which copy. This is the second copy, this is the 0th copy. And I mean, it's you might think it's sort of sorted kind of weirdly with the V2s and then the V0s and then the V3s and the V1s, but that's because of the shape of the differentials. Oh, actually, I don't know why I did that, but that's just the way I did it for some reason. This is just left in the left state that I had it, and I sorted it for some reason that way. I don't remember exactly why.
Yeah, this is great, actually. I never thought about doing this. One of the perks of just using Microsoft Excel is that you can sort by filtration, you can sort by stem, you can do it, of course you can.
Which
right?
is
That's
what I
great.
do all the time. Yeah,
That's great.
exactly. And it's just, and yeah, you can do this all, you can write code to do this. You can use Python to sort all these things too, right? Except, it's just much quicker and easier for at this level to do this sort of thing. Yeah. Yep. Okay. So that's that. Now let's get back to the actual talk. Okay. So the last time we met, I was making a case. I was talking to you about something about TMF, and I was making a case for the idea that one should study G-periodic phenomena in homotopy theory. And that's a little bit weird because classically G is nilpotent. And so G-periodic, there aren't any G-periodic phenomena classically, but motivically G is not nilpotent. And so you can make sense of that. And that's really what I'm talking about. And so then you've got we're familiar with V1 periodicity, and I think of V1 to the fourth as, I mean, I wrote it as a massive product, but really I'm thinking total brackets here. I'm thinking I'm writing Latin letters, but I'm really thinking homotopy elements, right? Okay, and then W1 to the fourth, you can define using a kind of an analogous total bracket. But classically, again, we say classically this is 0 by the sheet of nilpotent, so it's not so interesting. But when you work motivically, things are more interesting. You define G times X or X times G to be this total bracket. Okay, so G is not an element, tau G is an element, but G itself is not an element. And so we think of this really as an operator that's only defined on elements X that are killed by H1Q or by eta Q. Okay. And the upshot, I mean, I say this, but it doesn't follow from this, but it turns out that this G periodic homotopy or W1 periodic homotopy is non-zero. Okay. And the reason that I call it G, the reason that I call this total bracket G is because that's what it does on the map from the sphere to MMF. The unit map takes these brackets of this type to a primary product times G. So it's like a lift of G from T and from MMF back to the sphere. Okay. All right. So let's skip that. All right. So then we want to study W1 periodicity and see what's in it, like just, at large, like what can we prove about W1 periodic homotopy? Okay, so an obvious place to look is in Chow degree 0. So remember what Chow degree 0, Chow degree is you take the stem, you add the filtration, and you subtract twice the weight. It's some funny degree, but it has the property that in semotypic is always greater or equal to 0. And so Chow degree 0 is sort of one edge of the computation. And in particular, this operator G has Chow degree 0. Okay, so when you're looking for G periodic families, it makes a lot of sense to look with respect to Chow degree since G preserves the Chow degree. Okay, so the first place to look is right in Chow degree 0. Let's see what we can find that's G periodic in Chow degree 0. Okay, so and so remember there's this isomorphism between Chow degree 0 and classical X, and G, under this isomorphism, G corresponds to the Adams periodicity operator, capital P, or V1 to the fourth, okay? And so then there's the natural idea is to take the V1 periodic elements in classical homotopy and look at the analogous W1 periodic elements over here, okay? And so we talked about how Andrew studied the ones that are highlighted in yellow, okay? So the classical ones. Andrew studied these guys, which are analogous to the ones that are in yellow. And then I drew this little picture. This is the top of the Adams chart. You have this little motif that gets repeated every 8 stems, and Andrews handles the ones that are in yellow. He looked at he applied that isomorphism. He got these elements, and he proved that these are all infinite G periodic families in semotypic stable. Okay, but that leaves some elements. It leaves these 2 pink elements that he did not address. Okay, and all of these blue elements as well. That I have an arrow here because the length of this tower varies depending on the stem. Right, that's the image of J stuff there. Okay, so that's what we're going to do. We're going to look at the 2 pink ones and the blue ones. Okay, so that's our goal. Okay, and we're not going to resolve everything about the blue thing. We're going to resolve everything about the pink ones, and we're going to resolve most of the about the blue. Yeah.
Is it a coincidence that all the classes analyzed by Andrews are co-kernel H?
No, they're not, because, here, they're they're annihilated by H naught, but when you double them out to, using the isomorphism at the top there, when you double them, they become elements that are annihilated by H1. And that's what he did. He used the cofiber of eta. That's precisely what he did. He studied the cofiber of eta. That's how he detected these things. But then these are the only ones that he could detect with the cofiber of eta. See, this element isn't killed by eta. And so the way it shows up in cofiber, it gets a little mysterious.
So also at the bottom of the MJ tower, there's a hidden extension.
Yes, it has an eta, but when you double it, that becomes a new extension. And so, but anyway, but yes, that's right. Okay, so let's do this. Okay, so, what are these pink elements? Okay, so P to the K H2, P to the K H not H2. When you double them, you get H3 G to the K and H1 H3 G to the K. So those are the elements. Those are the first two types of elements that I want to study and figure out what happens to them in homotopy. Okay, so let's do that. Okay, so I need some general propositions, and none of these propositions are particularly difficult, and they all have analogs in V1 periodic homotopy. Okay, so the first thing is that if you have a permanent cycle in your spectral sequence, in your atom spectral sequence, you have an element you already know is a permanent cycle. Say it's in relatively low stem, so you've just computed it by hand and you see that it's a permanent cycle. Okay. And it's annihilated by, again, I wrote it as H1 cubed, but you might prefer to think of it as I'm saying that eta cubed times it is 0, right? I mean that it's annihilated by this is sort of in homotopy. Okay? If it happens to be eta cubed torsion, not every element is eta cubed torsion, especially not motivically, but some are, right? And if it is eta cubed torsion, then x G to the K is automatically a permanent cycle for all K. Okay, so this is a tool for generating G periodic permanent cycles. Now, I want to be precise what I mean by permanent cycle. What I mean by when I say permanent cycle, what I mean is permanent cycle. It is always a cycle. Okay, I'm not saying anything about whether or not it is hit by a differential. Things that are hit by differentials are cycles. Okay, so permanent cycle means exactly what some people use the word permanent cycle to mean like an element that's non-zero, but that's just not what those words mean. And so don't call it that. Okay.
Infinite cycle is what people use to mean what you just call a permanent cycle sometimes.
Infinite cycle means lasts forever and stays non-zero.
Wait, I thought that was a permanent cycle, an infinite cycle, man.
Oh, yeah, which is it? It's always hard.
Right, that's which proves my point, right? Like those are synonyms, right? That we're using in a different way. So okay, whatever. Anyway, that's what I mean here. Whether they're non-zero or not, whether they're hit by differentials, that's a separate question that we have to address. Okay, but all I'm saying here. Now, you might worry about, well, this H1 cubed restriction here, so it's not completely useful, but really it's not so bad because there's analogs of this proposition. If you have an element that's killed by H1 to the 7th, then it's going to be like G squared periodic. And if it's killed by H1 to 15, then it'll be G to the 4th periodic. So it works out okay. Given, as long as an element is killed by some power of eta, then one of these results will apply to it. And there are eta periodic things that won't apply, so that's have to be. All right, now, what about, so you get these elements that are infinite cycles or permanent cycles or whatever, okay? But how do you know that whether they're hit or not by differentials? Well, turns out there's this other proposition here that no element in Chow degree 0 is the target of an Adams differential. It's just simply impossible for degree reasons. Okay, Adams differentials increase the Chow degree, and 0 is the lower bound on Chow degree. So if you're in Chow degree 0, there's just no room for differentials that would have to come from negative Chow degree, and those simply don't exist. Okay, so that's the thing that makes Chow degree 0 particularly easy to work with. This kind of a proposition is not true in higher Chow degree. You look in Chow degree 1, elements of Chow degree 1 can be the targets of D2 differentials, which is not so bad because D3 and higher is ruled out, but it still can be the target of D2 differentials, and you have to deal with that. But in Chow degree 0, we did that for free. All right, so let's take a look at a concrete example. Okay, let's take a look at H3. Suppose you start with H3. H3 is a permanent cycle. We know already that H3 is a permanent cycle. And if you look at an Adams chart, you might think that, oh, well, it's killed by H1 cubed. That's what it looks like on the Adams chart, but there's a hidden extension there. Okay, and H1 cubed times H3, it turns out is actually non-zero in homotopy. It's detected by H1C0. Okay, so the hypothesis.
Is that in the right degree? 7 plus 3 is 10. 8 plus 1 is only 9. Is that H1 squared?
Yeah. Thanks. Which might puzzle you if you're thinking classically, but I'm not thinking classically. I'm working motivically, and H1 squared C0 is non-zero. Thank you. Yeah. Okay. So what I'm saying here is that this proposition does not, the hypotheses of this proposition don't apply to H3 because this does not hold, which means that H3G could potentially not be a permanent cycle. It's possible that, I mean, you know, the proposition allows for it, and it turns out that H3G does in fact support a differential. Okay, now the way I know this differential D2 of H3G equals this product here, the way I know this differential is through the algebraic Novikov spectral sequence, is a whole different story that I'm not going to talk about here today. But anyway, I know this differential for some other, you know, unrelated reason. I actually think.
D2 of H3 should be H not H2 squared.
Yeah, exactly, right. And in this sense, here it is exactly. It's related to that. Right? Yep. Okay. So all right. So fine. So now you have an element that does support a differential. So this proposition was about permanent cycles, but now we've got this H3G that does support a differential. So we would like sort of a proposition about how G interacts with differentials. This is kind of talking about how G interacts with things that don't support differentials, but we need a proposition about how G interacts with things that do support differentials. And that's what this bottom proposition is, that if, again, you still need this condition that X has to be annihilated by H1 cubed, but if X is annihilated by H1 cubed, then D2 on XG to the K is just D2 XG, just computes, okay? All right, so, and none of these propositions are particularly difficult. This is all kind of standard familiar material for people who study this kind of stuff.
Well, this is G is a permanent cycle and 11.
Well, but remember, G is not an element. G is a massive product operator. Yes. So it is, it's a higher Leibniz rule. It's exactly what it's saying, it's a higher Leibniz rule.
It doesn't have a lot bigger.
Exactly, so you gotta worry a little bit, but you know, basically it just, you know, it works out. Okay. All right, so the upshot of going back to this example is that this D2 differential actually generalizes to a family of non-zero, a G periodic family of non-zero Adams differentials. It's just a D2, but still it's a G periodic differential. Okay, and the whole point of the first talk that I gave in this mini course or whatever seminar series was about elements in Chow degree 1. Okay, and I studied this Chow degree 1 stuff, and I said there were two families of elements that I was particularly interested in, and one of those families was, if you go back to the notes or whatever, go back and look at it, this was one of the families that I studied. Okay, and that's why I got interested in Chow degree 1, because I knew this formula held in general, but I wanted to prove that it was actually non-zero for all K, that the target was non-zero for all K. And so that's where the whole Chow degree 1 study ended up coming out. And then we did prove that this target is non-zero. Okay. When you look at this H0, H2, H2, G to the K, the first thing I think of is I look at all those things and say, well, that's like TMF related stuff. That should be detected. That should be detected by you know, cohomology of 2, but it's not. Okay, it turns out that actually is this product actually is 0 in the cohomology of 2, the motypical C-motypical cohomology. So you can't do, so you have to do something. You know, that's kind of why I was sort of stuck for a few years, because like the obvious tool didn't work, and then I had to work a lot harder with this whole Chow degree 1 stuff that are, you know, that's not zero. Okay, so that's already pretty interesting. There's a G periodic differential in the Adams spectral sequence. I don't think that we knew that. I don't think we had an example of that until this one. I mean, you have V1 to the 4th periodic differentials in the classical Adams spectral sequence. Lots of them. That's kind of familiar and, you know, comfortable. But here's, you know, so this is kind of like that same phenomenon, but W1 periodic rather than V1 periodic. Okay, so that's what happens. So that's what H3G to the K, that was one of the pink elements that I wanted to describe what happens. That guy that Andrews didn't study because it was difficult, turns out it has more exotic behavior. It doesn't survive. It supports differential. So that's kind of, it's an interesting thing. And then the other, okay, so that's one of them. And then the other element that I said we were going to talk about is H1H3G to the K. H1 times it. Now, H1H3G turns out to be a permanent cycle. Okay, and it is annihilated by H1 cubed. And so then you apply those propositions and you get that H1, H3, G to the K is a permanent cycle for all K. Okay. And it's automatically, it's non-zero W periodic. It's exactly the kind of thing that we were before. Okay, so let's go back here let's go back here and kind of just see where we're at here. So this was the list of elements. Again, Andrews studied these guys. We just talked about this guy doesn't survive. This bottom one doesn't contribute to single-typic homotopy. This is, of course, what happens. This one, this H1, H3, G3K, this one does survive, and so okay, fine. And then so that settles those two guys. And then the last thing that we want to talk about is this stuff in blue. What about these? What about the doubles of these guys? Again, remember, that picture really corresponds to this side. We really want to double them. So that H0 tower becomes an H1 tower. We want to study these H1 towers and how long are they and where they sit and all that stuff. Okay, so that's the and I'm saving the best for last. I'm saving the most interesting part of this story for the end. Okay, so first of all, before we do that, let's go back and let's just look at classical V1 periodic homotopy. Okay, so I drew these pictures because I had to sort of sort out in studying the G periodic stuff. I had to get a very kind of good handle on the classical thing, and so I drew these pictures. What have I got here? So first of all, the numbers aren't the stem; they're like one more than the stem. Because it's all indexed by -1, and it's
boundary map.
yeah, it's just sort of annoying to deal with numbers like 7 and 15 and 23, and it's just easier for me to think about 8 and 16 and 20 and just see the multiples a little better there. The two-adic valuations are kind of the relative two-adic valuations are. So be careful. This is 15 stem. This is 31 stem and so forth. Okay, so I wrote down the names of the elements in the atom spectrum sequence to detect the generator. Okay, and then I drew them, with the sequence of vertical dots that indicates the order of the group. Okay, but one thing that I did is I sort of shift. You're used to looking at the Adams tower. You don't see the tops of these towers don't line up like this. I drew this kind of in a way that looks a little goofy from the perspective of the Adams spectrum sequence. Although I think it's kind of more familiar for people who think about these things in terms of the Adams-Novikov spectrum sequence. But anyway. So I wrote these all out, and then there's the orders, right? 3, 4, 3, 5, 3, 4, 3, 6, 3, 4, 3, 5, 3, 4, 3, 7. The usual kind of ruler, and you can see the usual ruler pattern there. I left that one blank because I know what that element. That's only the 47th step. That's not that far, but its name is kind of a strange thing, and it's not really very helpful. So I kind of left that one blank to avoid the distraction. And then the same thing here. I have a name for this guy in the 95 stem. It's just not very useful, and I didn't want people to ask annoying questions about it. So I just, so I didn't write it down. Okay, and the pattern continues: 3, 4, 3, 5, 3, 4, 3, 6, 3, 4, 3, 5, 3, 4, 3, 8. Right, when you get to the 127 stem and so forth. Okay, so a couple things about this. First of all, the reason that I lined these dots up in exactly this way is that V1 to the 4th acts horizontally. V1 basically acts horizontally. Okay, so what I'm saying is that if you take something like 4 nu is that guy right there, and you apply V1 to the 4th to it, you get 8 sigma. Okay, and if you apply V1 to the 4th, V1 squared. We don't really want that one, right? Yeah, all right. So let's do that. Let's do this again. If you take sigma and you apply V1 to the 4th, you get 2 times the generator in the 15 stem. Okay, and if you take 8 sigma and you apply V1 to the 4th, you get that
16 times the generator or whatever. Right? So V1 to the fourth lines up exactly in, in horizontal rows. And similarly, like V1 to the eighth is acting there, and V1 to the 16th is acting there, and so forth. So this picture is particularly good. While it doesn't agree with Adams filtration, it's very good at seeing exactly what we mean by V1 periodicity. Okay, and though I kind of think of this as like a two divided V1 periodic family, that there's all this V1 periodicity in rows, but it's kind of, they're becoming more and more divisible. I mean, in some sort of two-adic way, but that's kind of the way I would describe it, as some sort of like two divisible V1 periodic family. Okay.
That's how like the divided alpha thing.
Yeah, right, exactly, right. And that's what I meant when I said a few minutes ago that people who study this from the Adams Nova perspective, probably this picture is probably a lot more familiar, because I think it's more transparent in that you don't have to do all this filtration. It's kind of the way you calculate it. It just comes right out.
Well, curiously, in the Adams spectrum sequence for connected J, you do see that already
Yeah,
at E infinity.
yeah,
Because there's a filtration shift for
Yeah.
J, where the filtrations become very simple.
Yeah.
J.
yep. Yeah, I mean, that's, right. Well, the point is that this, the different tools see things in slightly different ways, and depending on what your goal is, specifically you're looking at, it could be more or less convenient, just depending on what is your. Okay, and then the other thing that I wanted, the other note, I don't know why it's note 2 and note 3 and there's no note 1, but that's some artifact of my editing. Note 3 is that there's two-adic continuity here, which is sort of fancy language for this idea simply that the order of the groups, it depends only on the two-adic valuation, right? That all of these groups, all of these guys in length 4, they all, when you add 1, there's, I'm trying to say, the number of dots here depends on the two-adic valuation of 96. The number of dots here depends on the two-adic valuation of 128, and so forth. That's all I'm saying. Okay, so I'm not 100% sure that two-adic continuity is the right word for this, but it's not that far off of the right idea. But anyway, that's just what I want that idea that things depending on the two-adic valuation of the stem. Okay, so now I want to look at something a little bit different, because it turns out that this other variation is going to be more relevant for what we want. I want to talk about algebraic V1 periodicity. Okay, so I'm not talking about stable homotopy groups. I'm talking about the Adams E2 page. I want to look in the Adams E2 page, and I want to look at these, at the same spots, but before we compute Adams differentials. Okay, before we compute Adams differentials in the 15th stem, what we have is H4. We have 8 elements, 8 H dot multiples. Well, 7 H dot. Anyway, there's H4 there. Now, yeah, H4 supports a D2, and the next two support a D3, and these are the only ones that survive to homotopy. But it's longer to begin with. And then this guy, instead of it being just 4 elements of dots, there's actually 6 elements, and this one there's 16, and so forth. Okay, so you can study this a ways. Okay, so that's the first 64 stems. Doesn't all fit on the screen. It's because this last one's so long. There, okay, and then there's the orders down at the bottom. You see every other one, there's the 3 that are familiar, and then there's a 4, but then it's 6, 6, 6. It sort of stabilizes as this one is exceptional, and then stabilizes, and then there's an 8, and then a 12, and so the pattern's a little bit more complicated than it was in homotopy, and that's good or bad depending on where things are headed. Okay, so what I wrote out here, I didn't draw the pictures, but I wrote out here the orders of those H naught towers, okay, in all these different steps. So what do you see here? So again, you see, okay, so look at the yellow, every other one is a 3, and then every fourth one, well, it's 4, and then 6, 6, 6, 6, 6. So there's some sort of like stable two-adic continuity where at the big there are finitely many exceptions in each two-adic level set. So if you take a fixed valuation, there might be exceptions at the beginning, but then it stabilizes. So like the pink ones stabilize with value 6, that's an exception. The blue ones stabilize with value 12, 8 is an exception. The orange ones stabilize at 28, 16 is an exception, so forth. Okay, so what's happening with these exceptions is that it's the elements Hn. Okay, those elements from this perspective, those elements are irregular. Okay, those are that 4 that's not 6, and the 8 that's not 12, and the 16 that's not 28. It's the HNs. Now, the HNs follow their own pattern, right? The old pattern is 4, 8, 16, 32, 64, and so forth. So there's like an exponential thing happening with the HNs, and then some other pattern happening with all the rest of them. Okay, so that's what seems to be, that's what's happening algebraically. Okay, so there's that. And then, so what this all boils down to then is sort of like the interesting cases are these first non-exceptional ones, right? So there's this one and this one and this one, right? That's kind of what we were interested in. What are those first non-exceptional ones? And when you do the numerology, this is the stem that comes out. Turns out you're interested in these stems 3 times 2 to the n minus 1. Okay, so for example, the 23 stem, the algebraic divisibility is 6. There's an H0 tower of length 6 in the 23 stem. In the 47 stem, there's an algebraic, there's an H0 tower of length 12. In the 95 stem, there's a tower of length 28. In the 191 stem, turns out there's a tower of length 58. Okay, and I'm giving some named credit there because it's only in relatively recent times that, like in the last few years, that we had enough data to actually see explicitly that thing. Okay, so that comes out of the Bruder-Dragos data set or the Chatham-Chua-Boye-Feist Tower data set. And we don't have time. Yeah, I was going to pull up a chart just to show it to you, but I think because I want to finish here by 3 o'clock here once and for all. So I'm not going to do that. The next one, 384 minus 1, I don't know. I mean, how does this sequence continue? 6, 12, 28, 58. What's the next number in that sequence? I don't know. Okay. And then, I mean, and that's fine. That's the algebraic, H0 period. The algebraic V1 period is C. But remember, this we're talking here about structure of X. And then, what about the patterns of atoms differentials on those elements? And if you go back here, you might be able to I kind of this pattern sort of this chart sort of shows the pattern on the first few, and you might be able to make some guesses or maybe not. It's kind of hard. I mean, you can kind of see, like, at the 128, you're going to see D2s, D3s, D4s, D5s, 6s, but exactly how many elements there are is a little bit hard to see exactly what's happening. I'm not sure that it's really I'm not even sure if it's knowable in any kind of reasonable sense. I don't know.
In all stems. I mean,
Yeah, in general. Yeah, I mean, in general. Yeah, is there a pattern? I mean, there must be some sort of pattern, but I don't know. Joey, you missed the best part. You walked out right when I talked about the tower of length 58 and the 191. So, okay. All right. So now let's talk about what happens when you apply this doubling isomorphism and you look for eta towers, okay, in Chow degree 0. Okay, so this is what you get. I've written here the names of the elements. There's the H1H3G that we talked about a few minutes ago, H1H3G squared. So the yellow ones are that family that we talked about earlier. And then there's H1H4, H1H5, some element I1, that's the double of I. And so forth. There's something here with some goofy name that's probably not so important, okay? And then here I'm writing down the orders, well, the eta orders, right? These are eta towers, right? I'm writing down the lengths of the eta towers in C-motivic stable homotopy. So here, this guy, there's a 3, and then there's a 2 in every other spot, which is already different in the image of J. The image of J had a 3 in every other spot. This has a 2 in every other spot, and the difference was that differential on H3G. If H3G didn't have that differential, then that 2 would be a 3. So that G periodic differential is having this effect on
non-stable.
So square knot is lowering the order in some sense. Square knot going from V1 to the fourth.
Well, yeah, there it is, yeah, but when you look at the other numbers, okay, so these we would expect to be 4, okay, so that one's lower because H4 doesn't survive, okay, so that goes down because the differential H4, but then this one is 6. This is the same as the algebraic periodicity that we just studied. It turns out that this element I1 where is it? There it is. This element I1 is a permanent cycle. It's in the 53 step. And I know that because I just, we've analyzed the whole spectrum sequence that far. We can just see brute force that it is. Okay. So these numbers are very similar to the algebraic V1 periodicity, except that because of this differential, these 2's are there instead of 3's. And because of the differentials on HN, these there's a 3 instead of a 4, there's a 7 instead of an 8, there's a 15 instead of a 16, there's a 31 instead of a 32, a 63 instead of a 64. So it's similar, but there's a couple of places where things are different. And then so this I1, so see what happens is that when you get to this, you have to sort of study this element using some other methods. But once you know that that's a permanent cycle, then you can handle all these other ones. Okay. But it's getting the kind of like the first one in a family that's difficult. You have to do some outside, some sort of outside work. Okay. So then the next one that comes into play is this one. There's an arrow here because it gets so long and it was just kind of cumbersome. But the guy at the bottom of that tower there, that one, you have to analyze it separately. Somehow you have to figure out whether it might support a differential. Some of these guys do support differentials, right? I'm writing it here. Some of them do support differentials and some of them don't. And you just have to decide what happens. So we did that. That's this theorem here. It's in the 107 step, which is getting pretty close to the edge of what I can do with brute force. But we have data for the C-motivic atom structure sequence, and we found this element in degree 107, 13, 60. And we looked at all the possible targets for differentials on that element, and various methods we've used to rule them out. Okay. And it turns out that this guy, this delta 1 H1 squared I1 is a permanent cycle. Okay. And so that's telling me that this number here really is a 12, not some other slightly smaller number. Okay. So there's a 12, there's an infinite, there's an eta tower of length 12 in C-motivic stable homotopy. Okay. And then there's a question mark here, because that's the first element of the sequence that I don't know, whose value I don't know. Oh, sorry.
Oh, there, I see it now. Okay.
Yeah. So I don't know that one. 15. Yeah, it's in co-weight 95, but that you could have doubled it. It's out near, it's out near around 200. Maybe past that, but anyway, I have no idea what happens to that. Okay. All right, so right, that's what this question is. How eta divisible is homotopy in co-weight 95? I don't know. Okay, so this guy, again, we're seeing stable two-adic continuity. There are, when you look at the yellow ones are strictly, constant. The pink ones, there's an exception at the beginning, but then there's a bunch of 6s. The blue ones, there's a 7, but then there's a bunch of 12s. The orange ones, there's a 15, and then there's something that's presumably stable, but I don't actually know what that value is, and and so forth. Okay, so you see that. We see that. And then the real question I have is, what are these numbers, right? The classical image of J, there's all kinds of fancy, statements about how these relate to, things that people talk about zeta functions and Bernoulli numbers and put it in the language of kind of number theory. And are these values that I'm getting here, are they something in terms of number theory? I don't know. Seems possible. I mean, I don't really have any evidence that they're number theoretic, but it has that feel. Okay. And if you don't sort of believe that there's really any number theory here, let me restate kind of all these results that I've been talking about, and I've been talking about semotypic homotopy. And you could argue whether there is or isn't any number theory in semotypic homotopy. But let me say that all of this structure that I'm talking about, you can also see these eta towers in the Adams-Novikov E2 page. Or maybe even to make it sound more like number theory, in the cohomology of the moduli stack of one-dimensional formal group laws. Did I say it correctly? Okay, all right. Now I'm talking about the cohomology, I'm talking about structure in the cohomology of the moduli stack of one-dimensional formal group laws. Well, there has to, of course, that's number theory. I mean, look at those, listen to those words. That's all, that was a number theoretic description in some sense, right? I mean, I'm looking for something a little more naive, like words like Mobius or, Riemann or, things like that. That's those are the kinds of things that I would, prefer to have, but still, that's there. Okay, but what do I mean by, just to be precise about what I'm talking about here? I'm talking about, the alpha one multiplication. When I talk about these eta towers, I'm talking about alpha one multiplications in the Adams-Novikov E2 page. And when I talk about G periodicity, what I'm referring to there is a certain kinds of Massey products. Okay, and I wrote this before, but just to remind you, beta of 16 just means it's some element in STEM 16 and Adams-Novikov filtration too. And I don't know exactly which one it is or whether there are multiple ones there or not, but it's just there's an element in degree 16, 2 in the Adams-Novikov spectral sequence, and an element in 32, 2, and so forth. Then so that's precisely what I mean by G periodicity in the Adams-Novikov page. Okay, so all this structure, these same numbers, these same length of eta towers are all showing up. Okay. Oh yeah. I kind of missed an important remark here. Number 2. I skipped over it accidentally. I mean, this is coming out very interesting, right? Look, so first of all, I have to, in order to get these results, I actually have to use that Mahol's results. This is not an independent proof that H1HN survives. Okay, I'm using that the classical H1HN survives in order to kind of not have to do some work at some point. Okay, so I just want to make that clear that this is no kind of reconstruction of Mahol, although it'd be sort of interesting to think about that, but I don't really have to do it. And then the other thing I want to say is, but these H1HNs, they are showing up at the bottoms of these towers. And so the Maholwalds A to J, they are a family. They are related. There's this H1 divided W1 periodic family. So what I mean is something like this. You take an A to J and you apply some big lots of G multiples to it, and you get some other element that's way much further out than the A to J. And then that element divides by eta down to A to J plus 1. And then A to J plus 1, you take a bunch of G multiples out to some much larger stem, and then divide by eta to get to A to J plus 2, and so forth. So the Maholwald A to J's really are an H1 divided W1 periodic family. Okay, that's not something that I don't think anyone was expecting to see that. That kind of just showed up at one point, and we're like, oh, well, that's kind of curious. Anytime you're finding a pattern, some structure to this, to the Maholwald A to J family, you're probably onto something interesting, because
So this is saying G to some large N, A to J is H1 to some large K, A to J plus 1.
Yes, that's exactly correct, 100%. And then there's other ones that are kind of interpolate in that family.
Yeah,
as
once
well.
you've got those, you
Yeah, there's
Well,
lots of other ones as well. Right. Okay, all right, and that's all I had to say. So thanks for sticking it out to the third and final talk. We made it, and I'll wrap it up here. Okay.